This is lecture number 17 in this course on electric machine design. If you recall, in the last classes we talked about the output equations for the DC and AC machines, and we mentioned in the previous classes that the armature power developed in the armature PA is equal to C naught times D square L times N, and for the AC machine it is Q, which is equal to C naught D square L N S. So if you see in both these equations, this factor D square L is present in both the outputs. So before we proceed towards the design, it is necessary that this product D square L be split up. And how this can be done is we need more data. Basically, more data about the design process is needed so that this factor D square L can be split up. So some of the factors which influence this the relative values of these D and L, we'll talk about them now. So the first is we will first talk about separation of D and L in DC machines. Okay, and the first factor that we should talk about are the machine proportions. So studies have from studies in towards studies in this machine design, we see that the machine length, the core length, it must be approximately equal to the pole arc, which is denoted by the following expression. The length L be equal to B, which is equal to psi into tau. Okay, where this psi is of around 0.64 to 0.72. So the ratio of length L to tau, of the pole arc is 0.64 to 0.72. But in practice, this L is slightly greater than the pole arc B. So this L by T is actually taken, L over T is taken to be equal to 0.7 to 0.9. So the ratio L over T is taken to be equal to 0.7 to 0.9. So this you can ignore. So it's simply the ratio of L to tau is 0.7 to 0.9. The next factor that we have to keep in mind is the peripheral speed. And these factors will be clear when we solve some numericals. So for the time being, just keep them in mind, and then when we solve some numericals, these will be clearer. The peripheral speed of the armature, denoted by VA, is given by pi dn, where pi d is the circumference, and this peripheral speed is sometimes a limiting value to the value of the diameter d. So this peripheral speed should not exceed should be less than 30 meters per second, because speeds below this do not need any special rotor construction. So if the speeds are below this 30 meters per second, then the rotor can be normally designed. But if the speeds are higher than this 30 meters per second or higher, then we have to use some special banding wires on the overhangs, and these have to be especially strong to tackle speeds higher than 30 meters per second. So we assume that this speed will always be less than this 30 meters per second. This is factor number 2. Factor number 3 is the moment of inertia. You know that the moment of inertia denoted by J, and this is not to be confused with the current density, which is also denoted by J. So moment of inertia is approximately proportional to d4 to L, d4 times d raised power 4 into L. So, and it's always desirable for machines used especially in control systems to have a very small moment of inertia. So when you have small machines which are meant for control systems applications, the diameter should be as low as possible, such that if the diameter is small, the moment of inertia comes out to be small. But for larger machines, let me write this here, for small machines, for large machines, as in a high impact load machine, you will have can be higher, the diameter d can be made higher. This is factor number 3. The fourth factor is the voltage between adjacent sections. So this core length L is also influenced by the maximum voltage that can be allowed between adjacent segments. So if this voltage between adjacent segments is denoted by this term ECM, that is equal to 2BGM times LVA TC, where BGM is the maximum air gap flux density under load conditions. This TC is the turns per coil. So this ECM is around 30 volts, BGM is around 1.2 Weber per meter square, VA is equal to 30 meter per second, and TC is 1 for a single turn coil. So this, when you substitute these values in this equation, you come to the conclusion that this L is approximately 0.4 meters. So this is only an indicative value, but for large machines, for large DC machines, they have large diameters than the core, than larger core length. So this is just an indicative value of about how long the core should be for typical machines under normal operation. Okay, so these are some of the factors which influence the value of the terms D and L in in the design of electric machines. So this was about separation of D and L for DC machines. We will now talk about separation of D and L for induction machines or induction motors. So for this, some things you must note. For minimum cost, the ratio L over tau should be equal to 1.5 to 2. For good power factor, L over tau should be around 1.02 to 1.25. For good efficiency, L over tau must be equal to 1.5, and for good overall design, L over tau must be equal to 1. So these are some of the values for these two ratios in case of induction machines. And lastly, we will talk about separation of D and L for synchronous machines. The first limiting factor is the peripheral speed. So in case of synchronous machines, if we select an upper limit on the peripheral speed, we can fix the diameter d, because if the peripheral speed is exceeded, the rotor may become distorted due to centrifugal stresses. So if this VA is very large, what will happen? A rotor may have centrifugal stresses, so this may happen. So the output, so what we do, we mentioned we write this output equation in terms of the synchronous speed. So sorry, the peripheral speed. We write the equation Q is equal to 11 times BAV times AC times KW times 10 to the power minus 3 d square L ns. This is from the previous, we have already derived these relations. So this is, we have derived these relations in the previous lectures. So we have also mentioned that this peripheral speed is equal to pi d ns. So if you substitute this, put in this value d in this above equation, we get 11 times BAV times AC times KW into 10 to the power minus 3 over VA by pi ns square lns. So when you substitute all of these values, it is 1.11 times BAV times AC times KW into 10 to the power minus 3 into VA square L over ns. So with this equation, we can basically get an idea about how much the length and diameter has to be set. Okay, so if you increase the machine rating Q, that will necessarily lead to increase in the D and L until the this peripheral speed is reached. So once this peripheral speed is reached, you cannot basically increase D. So the only way to increase the output is to increase the length L. Okay, so then increasing this L will have in its own set of problems. So it's always, you always have to make a trade-off and see what factor you increase and by how much you can increase the factor. So this is something that you must keep in mind. Next we have the number of poles. So if you remember from your machines course that the higher the number of poles, the larger the diameter. So what happens if you have a large number of poles? What happens if you have a large number of poles? The pole pitch is small, and if you use a small diameter, then the field coils do not have enough room. Field coils so therefore it is advisable to have large diameter for with a large number of poles. So the empirical relation for this is given by this expression tau over L is equal to 0.5 plus 6 over P. Okay, so depending on the number of poles, you select the factors tau and L. Okay, and lastly we have the short circuit ratio. For the short circuit ratio, we know that to keep it higher, basically this is in synchronous machine, so maybe we can skip it, but just since this is related to the introduction chapter, let me just briefly mention it here, but we can go into the details when we talk about synchronous machines. So in order to obtain a high short circuit ratio, what is required? Large core length should be used. But one must always keep in mind a shorter core length since it is easy to cool a core with a shorter length. So and it also has another advantage of it also has the advantage of having high critical speed, and also it reduces leakage between pole bodies. So more on this topic when we talk about synchronous machines. So just this is just some points I would like you to keep into consideration before we go on to actually talk about design of specific machines. So with this we come to the conclusion of this basic introduction part, and what I would want you to do is I would want you to solve some numericals. I will show you one problem right now, and I would want you to try some more problems at your own places. So let's see one example. Suppose you are given two DC motors and they run at the same speed and they have the same poles. The physical dimensions of these machines are in the ratio of 3:2. So what we are asked to compare the outputs, the iron losses and the copper losses. Okay, so we are asked to comment upon the two when we are given that we have two DC motors which have the same speed, the same number of poles, and the physical dimensions are in the ratio of 3:2. Okay, so you also have been asked to mention any assumptions that you make. Okay, so if you go back to the previous lectures, you will see that if you have machines in the ratio with dimensions x in the ratio of x is to 1, the outputs, right, the outputs are in the ratio of x4 is to 1, and losses are in the ratio of x3 is to 1. We've already discussed this in the lecture. So what are the assumptions? The assumptions are that the specific electric and magnetic loading are the same. Specific magnetic loading and the specific electric loading, these are the same. So when you have a machine with dimensions in the ratio of 3:2, what is the ratio of outputs? Outputs are in the ratio of 1.5 raised to power 4 into is to 1, or 5.06 to 1. The iron losses is 3.37 is to 1, and the copper losses are also in the ratio of 3.37 is to 1. Okay. So for a machine with dimensions in the ratio of 3:2, the losses are in the ratio of 5.06 to 1. The output is in the ratio of 5.06 to 1. The iron losses are in the ratio of 3.37 to 1, 2 is to 1, and the copper losses are also in the ratio of 3.37 is to 1. Okay, so let's try another problem. And the problem is like this. You are given a 11 kilowatt machine, 3 phase, 4000 volts, 50 hertz, and 1000 rpm induction motor. So these are the ratings mentioned to you. The I square R losses in this machine are 950 watts. The iron losses are 500 watts. The friction and windage loss are 110 watts. We have to find the output losses and efficiency. We have to find out. We are given that the machines are linear dimensions in the ratio of 1.5 is to 1. Okay, so we have to then compare the efficiencies of the two motors. Okay, so what is this? When you say that you have to find out output losses and the efficiency, these values which are given to us, they are from a particular machine. We have to find out the output losses and the efficiency of a machine with the dimensions of in the ratio of 1.5 is to 1. Okay, so let's see what are the total losses in the original machine. So they are 950 plus 500 plus 110, so that's 1560 watts, and efficiency is 11000 over 000 plus 1156, so this is 0.876. So the ratio of friction and windage to total losses to the output is about 110 over 000, so it's about 1%. Okay, so this is for the original machine. We know that the output varies as the fourth power of the linear dimensions, so output of second motor is 1.5 raised power 4 times 11, so it is 55.7 kilowatts. And then you have the I square R and the core loss. They vary as the cube root of the linear dimension, 1.5 cube times 950 plus 500, so it is 4893 watts. And the friction and windage is equal to 1% of total loss of the output losses, so that is 1 by 100 times 55.7 into 10 to the power 3 this is about 557 watts. So the total losses for this second machine are 557 plus 4893, so that comes to be around 5450 watts. So the efficiency of this motor is 55700 over 700 plus 5450. This comes out to be 91.5%. So this is the efficiency of the second machine. So I hope you have understood this. You can rewind this video and play it again to try and understand what I am trying to tell you, and I would encourage you to solve more problems. And in the next lecture we will shift to armature windings. The next few lectures are going to be very intensive, and I would want you to watch this video as soon as possible before we go on to the next set of lectures. I will see you in the next lecture now. Thank you.